This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Now, you all are going to have exactly the same feeling that a lot of other people have said when they asked, what in the world is an astrophysicist doing chairing a session on oceanography? And the answer is that Wolf Berger, who was scheduled to do this, was unable to make it. So we self-organized at the last minute, and I'm your chairman, which is why I'm here, and that's the only logical explanation I can offer. So, so we have a self-organized session, and the only thing I know is the order of the speakers, and I know 2 of their 3 topics. Walter Munk, who will go first, I asked him what he was going to say, and he said it's a secret. And so he's earned the privilege. And so then next is John Orcutt, with whom I worked exceptionally closely when he and I were in the director's office together. And he's going to talk about the Arctic, which will be a nice lead-in to one of the talks that we will have in my session tomorrow. Yeah, I mean, it's coming up. I think my talk is prepared. I'm not sure, but and then finally, Lynn Talley is going to talk about ocean circulation and the real topic of this session, which is the oceans. So with that, Walter, I'm as eager to hear what this classified topic is as everybody else.
You will soon see why I wouldn't reply to Charlie. You see here my first slide, and everyone else so far has started by complimenting Charlie what a great job he did in various aspects. My first slide was stolen from Charlie from something he spoke about a few months ago at the Vatican. That is a slide that Charlie showed on his most recent work on the hiatus of global warming. And you see there are 2 periods, one starting around 1960 and another one starting very recently, about 2005 or so, where the temperature of the atmosphere and of the surface water did not change at a time when the CO2 content of the atmosphere was continuing its unstoppable, continuous increase that it has done since the turn of the century. And people who would like to find a fault with the global warming point of view could point to that and say, you see, there has been no warming for 10 years and CO2 has gone up. What's going on? And Charlie has written a very detailed paper on that subject, which is being published by the Vatican, the American Philosophical Society, and has related that to an El Niño-La Niña cycle, having looked into many possibilities. And I want to point out that I think he's absolutely right. And I will show you slide 2, which I was permitted to show by courtesy of Dean ROEMICH and John Church from Australia. And it goes back to something that was discussed earlier this morning, Argo floats. You know, there are now 3,600 Argo floats. You've seen a few pictures of how they're distributed over the world's ocean. They go down to 2,000 meters and then stay there for 10 days, then go up to the surface and give the information of what they measure on the way down and on the way up to some satellites. A hugely successful undertaking. And this is an unpublished slide of what they have observed to 2,000 meters. And it shows that in that deeper column, the heat content, which is the proper variable, not the surface temperature, but the heat content, has in fact increased over this period, even though surface temperature, as you can see, remained relatively constant. And it looks on that slide as if this year will in fact be the end of constant surface temperatures as well. And it's in complete support that there is a warming of the heat content of the planet Earth. And the interesting thing is that it is now going deeper to 2,000 meters. And the reason for it going deeper has to do, in fact, with the El Nino, La Nina circulation, which Charlie discussed. Please let me discuss a table which I think is very interesting based on the Dean ROEMICH data. On the left column are heat content at various depths in joule, and the change in heat content in joules per year. And in the last 10 years, from 0 to 500 meters, 3 times 10 to the 21st, and almost the same amount from 500 to 2,000 meters. That's an enormous change, isn't it, Charlie, in the point of view that people have taken. You cannot interpret the unbalance in radiation without looking at not only at the surface layer of the ocean, but you have to now go down to 2,000 meters. And maybe essentially we have to go deeper. And those numbers are very encouraging. 6 times 10 to the 21st joules per year. When you ask what it demands for the unbalance, you get roughly 0.55 watts per meter square, which is a very respectable number in terms of what we know. It corresponds to certain numbers of degrees per year. And if you calculate the total thermal expansion for the whole water column 0 to 2,000 meters, using the Argo data, you come out with 3 millimeters per year as the contribution to global sea level rise from thermal expansion. It's not the major component of sea level rise, but it's a very significant amount. There is a further amount from the melting of land-based glaciers, which is not contained. And I was surprised at the magnitude. Now, if you look to the right, it has an equally interesting and unsuspected conclusion. It looks at the distribution not with depth, but with latitude of that increase in the ocean's heat content, and almost all of it is in the southern hemisphere. I don't think that was anticipated by anybody. Did you know that that would come out that way, Charlie?
No, but just 2 days ago, there was another paper that made exactly the same point.
With Argo data?
Yes, everybody's using Argo data.
Oh, I'm sorry. I thought I would show it for the first time with Dean ROEMICH's thing.
You got to move faster.
So that is really a basic step forward in understanding global warming, and it does support, in fact, the theory that people have had. Now, I have been an advocate of using acoustics as a way of measuring large-scale warming. And I have to tell you a few things about this particular method. It has turned out that low-frequency acoustics is remarkably well propagated in the ocean because of the existence of a waveguide, typically at 1 kilometer. A minimum in the speed of sound. The speed of sound increases upwards because it gets warmer, and downwards because the pressure increases. And in 1960, Maurice Ewing, who had discovered this sound channel, in fact, had his brother working near Perth, Australia, on a geophysical experiment. And he was looking at the map of the Earth and called up his brother John and said, "Looks to me like I ought to be able to hear you. Why don't you boys drop a few sticks of dynamite in the water and let me see whether I can pick them up in Bermuda?" 3.5 hours later. And they did drop 200 pounds of sticks of dynamite 3 times. There were no inhibitions at the time. It was a better time. And 3.5 hours later, this is what Maurice Ewing observed. In each case, there were 2 arrivals, and they were clearly received in Bermuda 3.5 hours later. And it turned out nobody published that result for years. And then I got a hold of the data and published it and explained why there were 2 pulses each time and gave the wrong theory. I said it was because there'd be a reflection from Bermuda, which would give a second arrival a few seconds later. It turns out that the real answer for the dual arrival is shown really by the great circles in the lower figure. Notice that between Perth and Bermuda, you can draw some great circle routes. One collides with the Cape of Good Hope, but just seems to barely go by, not very well. The other one to the left collides with Brazil, and somehow or another we had to figure that sound had a way to get through. I've mentioned nothing about Kerguelen, which gets in the way as well. And so nothing was published, and we, as I will show in the next slide, based a future experiment on that. Now, in recent days, a former Scripps student, Brian Duchamp, has studied this in great detail, and he used what is now available 5-day ocean temperature salinity charts from which you can compute the sound speed and allow for refraction. And he found that over a period of a month, sometimes the rays that are drawn here would wiggle back and forth through that narrow window. Sometimes they would miss the Cape of Good Hope and get through. At other times, they would miss Brazil and get through. But they got through only a few days a month. And could it be that Maurice Ewing, who was incredibly lucky, had just picked a few days a month when the refraction was suitable? And we still do not understand what really is going on. It's an interesting experiment. The real explanation for the dual arrival is that the ray near the northern ray comes in a little sooner and by the right amount than the southern ray. In some ways, you have apparently 2 arrivals, a Cape of Good Hope arrival and a Brazil arrival. Now, the advantage, what this suggests is that a repeat of this experiment could give you a 1-figure number about global warming. Global because it's halfway around the Earth. And from a time point of view, it's 50 years. So it's through most of the Industrial Revolution. And the difference in travel time is 10 seconds. It would today come in 10 seconds earlier because the ocean has gotten warmer. And it'd be such an easy experiment, and it would perhaps convince some people. And in a way, I like it as compared to the Argo floats, because it is integrating by its very nature. A single number has integrated over the path from Perth to Bermuda, whereas with the Argo floats, what they do is to average each month all Argo floats within a degree square. And so in different months, you have different instruments in that area. And I find it a little more satisfactory to use an integrating measure like the travel time as compared to averaging random floats in the area. Now, encouraged by that experiment, we performed a little later the Heard Island experiment. We used a loudspeaker, the electric source that was furnished to us by the Navy, went to the Heard Island in the middle of the Indian Ocean, and it turns out that from that location, you actually have great circle routes into the Atlantic via the Cape of Good Hope in Brazil, into the Indian Ocean, of course, and into the Pacific Ocean, especially by a window between New Zealand and Antarctica. And we managed without any bureaucracy, to persuade 12 colleagues around the world to take their ships out and lower a hydrophone into the sound channel and listen to us starting our transmission on Australia Day. We had great difficulties because it turned out at the time that various marine biological groups opposed it for a legitimate fear that the intensity of the sound would be harmful to marine mammals, to whales. And we were asked to take 2 ships, one to observe the marine mammals in the area, another one to have the hydrophone and have the acoustic loudspeakers that we used. And we had the obligation, reasonably enough, that if the biologic observers would find any indication of marine mammal discomfort, that we would have to cease our experiment, and there were no such indications. And so from one point there, we could really start observing all the oceans, and we have drawn sort of speculative plans to make a deep sea network of sources and receivers. You need only one or two dozens to really get good averages for all of the ocean basins of the world. And I'm still hoping, years later, that we could persuade the authorities to permit that. It would be a nice augmentation of the Argo floats to have the 2 methods of, and I think it's going to be essential in the next 30 years to measure the heat content of the oceans. Well, people will get worried about climate change, and they will want to know where the heat is going. And I'm hoping this will be possible. Thank you.
I would just add that there will soon be a conference on this whole method and redeploying this acoustic measurement of thermal content. Isn't that correct?
Yeah, I forgot to add that there is one problem. The Ewing experiment did not do good navigation, and there is a difficulty in re-establishing the exact positions where the dynamites were dropped. However, you could do the Heard Island experiment over again, and there are some thoughts of doing that.
Thank you. I'm John Arquette, just introduced. I have been, I began my work career as a nuclear submariner in the Navy and left submarining as a commander in the USN in 1972 and came to Scripps to do a PhD, which I completed in '76. And my subject was marine or ocean seismology in particular, and the structure and dynamics of the long volcano that represents the mid-ocean ridge was the subject of my work, and some of the fun things that I got to do was submarining again, for example, with my partner Bob Ballard, and discovered at 21 North in the East Pacific Rise this fact of black smokers, very high temperature vents in the seafloor, and so on. And then subsequent to that, got involved a lot with the monitoring and verification of test ban treaties. In fact, fairly early when I was director of IGPP, we had a substantial program with the Soviet Union developing confidence building measures associated with how large nuclear tests actually were in the Soviet Union. And then perestroika happened, and the world changed a great deal, but still the institution does continue to operate about a third of the global seismic network around the planet, which is kind of an unusual thing for a university to do, but we do. These long-term measurements have become pretty critical. I was the third director of the Institute of Geophysics, Cecil and Ida Green Institute of Geophysics and Planetary Physics. Walter was first, Freeman Gilbert followed, and I was the third director for quite a long time here. When Charlie came, he asked if I would be interested in being his deputy, and since I knew where all the skeleton closets were at IGVP, I thought I'd find out where they were around Scripps, and for better or for worse, I'd probably learned all that too. It was a very interesting experience. We had a lot of things to do and lots of opportunities. Those were back in the days when we had a budget in Congress, and we actually knew what the budget might be from year to year, and that there might actually be changes. But so in that sense, all those years of working with some level of management here, we had new opportunities almost all the time. And things have changed. We have more limitations today than we did even 3 or 4 years ago, but there are also still some great new opportunities. One of the things I just began to do is starting a new journal in the AGU, which is named after, it appears, the department at UCLA, Earth and Space Sciences, but the goal of the thing is actually to provide a venue in which people can publish papers on things having to do with Earth and space systems, but also concentrate on the background, that is, the things that Jeff Dozier talked about, these ideas of how do you actually get from measurements that are made on a platform to things with which you do science. That is, how do you understand the instruments that you're using? How do you understand the processing that goes into a problem? Even what's the code used and what is the advantage? So it's a rather new departure here, but we in earth sciences, I think, and ocean sciences for decades have not had a particularly good reward system for those who spend time working on the nitty-gritty of how do you make a measurement, how do you build an instrument, how do you actually reduce the data that are the raw data that arrive here. So I hope those of you in the audience that are here and have interest in publishing such things will get in touch, and we have started accepting papers on the 1st of August, and I have about 5 of them in process now, so I hope that the journal will become popular in the earth sciences and the AGU. Lou, I think, Lanzarote earlier commented on the spatial and temporal inadequacies of modeling, and they're problematic. The skill of climate models in predicting 10 or a decade or 20 years into the future are particularly limited. And so the talk that I'm going to give is going to be pretty relentlessly observational here. And just to acquaint you with the Arctic, this is some of the names. The Kara and Loptev Seas are important in this. The Beaufort Sea off Alaska is important, but you don't have to memorize, and there won't be any kind of a quiz associated with this. So this just shows you what the Arctic looks like, but the sea, the ice is changing substantially with time. And this just gives you an idea from '83 to 2011. Particularly the graph, which is on the bottom here. These are graphs through time of 5-year-old ice, 4, 3, 2, and 1-year-old ice, and you can see that relentlessly that the old ice is disappearing and moving out of the Arctic every year, and the size of the 1-year ice has been substantially increasing. So it's becoming a smoother, younger, ice-covered ocean. But Walter brought up the issue of how do we measure the heat content in this environment. It's very difficult with substantial ice cover to use the Argo floats, and he proposed, of course, not surprisingly, that we should think about the acoustic approach to doing this. This is another picture of what's been going on with sea ice. That graph at the top with the black line here is an average over 1981 to 2010, and this is plus or minus 2 standard deviations of the curve. In 2012, the ice cover in the Arctic reached its largest known minimum in that year, and we haven't seen that since. This is a couple of days ago what the ice cover looks like now, and you can see it's well above the ice cover that was present 2 years ago. So we don't know what next year will be like, but certainly we've departed from what might have been thought to be normal in the past. This just shows you again the ice extent in a few days ago here, as well as the mean ice coverage for this time of year, median ice coverage this time of year, averaged over the period 1981 to 2010. But the picture that you get is quite clearly changing, and one way to really get a feel for this. These slides that I'm going to show you came from Larry Mayer. He's a scientist at University of New Hampshire. He's a student of Scripps, but his profession now is the details of the seafloor, the deep seafloor, multi-beam mapping at very high resolutions. And he has been, for the last several years, working on acquiring data during the summertime in the Arctic. And so this is a picture of the bow of their ship heading into the ice in 2007 at about 20 degrees south of the pole. So this was some time ago in 2007, not that long ago, only 7 years. And if we take a look in 2012, that spectacular year that I showed you earlier, this is precisely the same spot, different ship, but there is absolutely no ice cover in this thing. If we go about 60 kilometers to the north, this is what it looked like in 2007. Here again, ice covered And if we go look at it in 2012, it's an open ocean. So this is just a graphic. It's a mariner's view of what it means to have no ice cover, but it's bringing a ship to these things to understand it. The goal he has, of course, is to map as much of the offshore topography as possible during these periods of time, and he collaborates with the Canadians who actually have an operating icebreaker to collect these data. He follows with the ship with the multi-beam, he follows the icebreaker during this period of time. At this point, he has measured about 40% of the American and Canadian, North American ocean up to the North Pole. So a proposal that a number of us are working on at the moment is a cable which would go from Barrow through the North Pole to Longyearbyen, where our Canadian colleagues have a number of stations, plus very, very good internet connections and cabling into Longyearbyen. Barrow is more complex. There's because the ocean retreat or the ice retreats so much every year now, the erosion along that coastline is tremendous, and getting a cable ashore and keeping it there for decades is not trivial from the point of engineering. But we're proposing this particular experiment over a very long period of time. This is just a fanciful cartoon of a cable with a repeater, which happens every 75 to 100 kilometers in this thing that has capability with communicating with systems that are outside through acoustics or blue-green laser or blue-green light to operate a variety of different experiments. This thing that I show you here is a transponder that is meant to represent the system that Walter talked about. The actual source, the actual transducer itself, is not remotely as attractive as that, but it's a good artist perception of the idea. There are a number of potential sensors on the seafloor, and these systems here, and here are actually used with the tomographic experiment to measure the position of that transponder accurately in the water column. You have to know the position of that transponder to approximately a meter in order to measure a average temperature change of a millidegree over several thousand kilometers, the kind of source receiver distances. But all those different systems that would be on the seafloor in the Arctic using this approach would support not just the thermometry or the tomography at these sites, but they would also be able to support regular, normal oceanographic observations and gliders, for example, that could be used to actually profile physically in the Arctic without coming to the surface, which is largely generally occupied by ice. The people up here, some of the people that are involved in this, Hanne Sagen is in Norway, and we've discussed this with the foundation, that Science Foundation in Norway, and they're interested in being partners. Art Bageror, Peter Michalewski, Peter Wooster have done a lot of work in the Arctic. Peter, in fact, now is in north of Tromsø, putting in a 3-year Navy experiment to do thermometry in the Arctic to repeat some work that Peter Michalewski did years ago. So heat content can be measured this way. It's a geophysical approach to doing this. Walter's explained it somewhat, but certainly in seismology, tomography, looking at the aspherical variations in the Earth is a very common tool. Carl Wunsch has told me twice now that he thinks that tomography is too complicated for physical oceanographers. They can't really deal with the complexity of this, but I don't believe that's actually quite true. But this is what Carl keeps insisting to me, that it's too complicated. I think it's not. Anyway, that's a proposal. We're working on it, and I think it's critical as the Arctic changes so much over the next several decades that this Arctic Watch be put in place, and the kinds of oceanographic sensors that we can use to measure what the satellites cannot measure are critical to our future. Thanks.
Thanks so much, Charlie and Ellen, for inviting me to come. There was a charge to talk about where do we come from, what are we, and where are we going? I think that comes from Gauguin. And there's actually a song or a round I could lead you in, but we won't. Where I'm coming from is following Walter and John, which is a pretty heavy-duty thing. And where we're standing is here, and where we're going is to dinner. So I'll try not to. Okay, so I'm a physical oceanographer. I've been here 30 years. Wow. What I do will become evident, I think, as we go through here. So I will move on. I'm going to just tell you what the final messages will be, because I have, as usual, too many slides. Number one, as you've already seen, global warming is ocean warming, and we will show you the numbers from that. Number two, so that's going to be probably that'll be my last topic, but I think it's the most important message. Second is I was asked to talk about what I thought was interesting to me over 30 years, and I'm a very large-scale oceanographer, and so the global scale of the ocean circulation is what's been interesting me, and there's been an awful lot of work on that over the last 30 years. Especially, I'm going to move from the Arctic down to the Southern Ocean here, the area which is around, we call the Southern Ocean is around Antarctica. It's critical to this global scale circulation. And that region affects the Earth's climate, it affects the sea level through its changes, its effects on the ice sheet at Antarctica, and on carbon balances and on productivity of the ocean. I won't go through all of those things, but I just want to make the point that the Southern Ocean, which is really far away and usually not in our minds, is extremely important for our Earth's climate. And it's already been alluded to, Charlie already mentioned it, that the paper that came out 6 days ago shows where this amount of heat in the Southern Ocean. And lastly, I'm an observer. I want to make sure we say, as John has just said and Walter said, sustained observations are key for monitoring and understanding how the climate is changing. It's important to keep the innovation going. Sustained doesn't mean static. And especially important to keep moving towards even more autonomous instrumentation. Argo is great, let's build on it. And areas that are tremendously undersampled that are important for this climate question are the deep ocean and the Southern Ocean. So that's basically where I'll end at the end. I would just want to talk a little bit about where I came from. There was, because I want to tie this into space. This is pretty much it. But back in 1957, there was the IGY. And there was this Sputnik. And that's all that most of us in that, who were children then, knew about IGY. But that started a real explosion in science education in the US. And I think that that made a huge difference for our generation coming along in the 60s and 70s in grade school and so forth. Education matters. And the education was irrespective of gender. So girls got treated like boys, at least in my school. And the space race was on. So off we went. That's pretty much it. There I am. I didn't want to work on astrophysics because it's my dad's interest. But I like to get my hands dirty. So there we are, building dams in the stream. The other thing that was really important, I think, for our generation of women, and I'm at the end of my career now, was that there was a feminist movement, a women's equality movement in the 70s, before it got a bad name. And it was important that we learned that we can do it, and that we weren't discouraged from following what we wanted to do. Until I got on my first cruise on a Woods Hole ship in 1978, and my second cruise on a Scripps ship in 1984. But that was long after I'd chosen to be an oceanographer. So, and things have really improved on the ships. The other thing that was important in the IGY, which I only learned much later, pretty much after getting here, was how important it figured in ocean science. And there's Roger Revelle, who was the chair of the panel on oceanography of the US IGY committee that year, and that started the big carbon measurements, and I'm sure you'll hear more about that tomorrow. And there's Dave Keeling, hired basically then to head the atmospheric CO2 program. So that started a lot of involvement in Scripps. And then I had one more legacy thing. Scripps has a legacy of female physical oceanographers that goes back longer than Woods Hole. Margaret Robinson and June Petullo was the first female PhD in physical oceanography from Scripps. And there was sort of a trickle of women along through there, and then the floodgates opened. Terry Chereska and I were the first, were two that arrived at Woods Hole together. Terry is here, working here, and Nan Bray was just 2 years ahead of us, and she worked here for quite a while. And Nan was the first PhD from Woods Hole. So from there, moving on here, I would say it all came together: space, oceanography, women's rights, and science education in the christening of the Sally Ride just a couple weeks ago up in Anacortes. So I think here we are. So that's kind of where things came from. What do I do as an oceanographer? I work on really large scales. There's the Palmer. This is an icebreaker that was in Hobart. This was last winter, actually summer there. I am a co-chair of the U.S. program that operates a global scale repeat survey. We did a lot of surveying of the oceans along all of these lines and many more in the 1990s in something called the World Ocean Circulation Experiment. And we have been continuing to do this, these measurements along select lines, and this is the network that's currently done. The red lines are the US lines, and that black line in the middle, right there, is a section I was on in March. What do we do on this? These are the gold standard of measurements. These are still ship-based measurements. We go out, we make the highest accuracy. It's really important to have a big network of things like Argo floats, but you still need something to calibrate and judge everything by, and you can't measure all the chemistry that's necessary for understanding climate change. So this is a network for doing that. Top to bottom, highest standards. And so here went our cruise last March, coming out of Hobart, off to the left, zooming south of the New Zealand EEZ, down to a point in the Ross Sea, and then we zoom north to Tahiti. I'm showing an altimetry image, actually. This is showing, we've heard about altimetry a lot already. This is a big eddy field. It's not the actual circulation, it's the eddy part of the circulation. It's very vigorous in here. This is the Antarctic circumpolar current coming through here, eddying lots of noise. That's the last noise I'll show you. I work on large-scale things that are pretty smooth. But every time we look at our data sets, we have to be aware of this very vigorous field, and it shows us how strong the currents are. The currents are very unstable through here. We measured from the Ross Sea north. This is the group. This is our measurement equipment. There's a few people sampling. Mark Warner, who was Ray Weitz's student here, he's been doing CFCs and data collection of samples for lots and lots of chemistry. And there's our group, and you'll see a lot of women in there. Things have changed a whole lot. Here's an example of the kind of data we collect. This is very, very traditional data. This is from the Ross Sea north of Tahiti, temperature section. There's a big ridge that's a big feature that the circumpolar current tracks on. You can see warm, red warm water at the surface, cold blue water at the bottom, very cold water in the Ross Sea. And what we can do with this very accurate measurements is compare them with every occupation before and show that there are temperature changes. I won't go through all that with you, but you can see the temperature changes in the distribution of them, especially this bottom water in the Ross Sea has been warming measurably even in the last 3 years. You can also look at lots of chemistry. I'm showing oxygen as an example. You can see features that track with the circumpolar current. The eddies are there. That's this sort of bumpy stuff. But this basic structure is there every time we measure, and then we can compare what happens year in and year out. We're also making measurements now from this program of new tracers. This is sulfur hexafluoride. This is measured as part of the CFC suite of measurements. This shows you where water was in contact with the atmosphere not too many years ago. So you see a big blank where there's older water, and then where there's color, there's newer water. So here's some bottom waters in the Ross Sea. Here's the thermocline, the upper ocean in the South Pacific, and then a very squeaky thin layer here in the Ross Sea that's exposed to the atmosphere. And then you can make lots of different choices on how to calculate where anthropogenic carbon is in here. This is the carbon from the atmosphere that makes its way into the ocean. This is one particular type of calculation, but I just think it's a nice pattern. You see it actually kind of looks a lot like this tracer. That's not coincidental. But there it is sitting in the upper ocean. This is where most of the exchange with the atmosphere is, but you can see some down there in the bottom of the Ross Sea. So you can find out where things are going into the ocean. That's important for understanding how the climate is going to change, or is changing already. So that's just an example of the large-scale stuff we do. There's tons and tons of examples. The other thing we did on that cruise, which is new, and I'm going to be moving into this with some new funding that's just arrived this week, is to build on the Argo program, which is this extremely successful global profiling float program, and expand it to a biogeochemical program. This is with a team headed by Jorge Sarmiento at Princeton, and Ken Johnson at Mbari, who's developed a pH sensor and nitrate sensors, and Steve Reiser, who will be supplying floats, and then we have a large modeling component. I want to point out there's a picture of the float, and we got dispensation to sign it, so everybody on the ship piled on and put their graffiti on it. And this is the emergency stop button. This technology is invented here. A lot of very important technology came from the labs here. This is Russ Davis in the 1990s as part of WOS, and that's what transitioned into the Argo program. Dean Rempick's extremely influential in getting that to go, a major vision to put this project out there in the global ocean, measuring the upper 2,000 meters. So the picture actually that really Ken Johnson has by developing these sensors is that this is the time to go and start measuring all the other stuff that we can do with autonomous sensors. And so this is what we deployed also from that cruise. Came down from Hobart, and this is where we put some floats in. Each color is a different kind of float. And the program will be called the Southern Ocean Climate and Carbon Observations and Modeling. It involves a bunch of people here and across the country, especially Princeton and UW. And this is our vision. It's kind of a sparse array for the Southern Ocean, but we'll be covering it, and they'll be sampling frequently. And here's some pH profiles. This is first ever kind of type of data from the Southern Ocean. This is a slide from Ken Johnson showing pH on the floats that we deployed. South of the polar front, north of the polar front, and the number of profiles that we collected in 1 month south of 40 South was more than had been collected in 30 years in that month. This is really important because the Southern Ocean is one of the areas that's acidifying faster than other areas. Breakthroughs. Global circulation, Southern Ocean. We know where the water goes. I'm going to segue, jump fast, away from what I measured to what I think I like to look at. Global ocean circulation. You've probably all heard about conveyor belts. I'll show you. There's the conveyor belt. This actually came out after my career got started. So 1987, Broker conveyor belt. Lovely thing about this diagram is it shows the connectivity of the world, that all these oceans are connected. It's an awfully schematic version of that, but if we go back, what we could say about the world ocean is we know pretty well where the water sinks, because it sinks in local places where it gets dense enough. But figuring out where it comes back up again has been a long chore. And probably 20 years ago, he was said, "Well, really don't know." And the idea of Walter and Hank Stommel and so forth in the 50s just say, "Well, it's coming up everywhere." What we know now is that the Southern Ocean is extremely important for where water comes up. Palachesi, who's here, maybe someplace, has been working a lot on modeling. There she is back there. We know that this region is critical for very specifically well understood dynamical reasons. So this was the conveyor belt that Wally Broker brought us. He knew there was a Southern Ocean, but he wanted to simplify something for a magazine, and there we got it. We got stuck with this picture, and then I kind of stick my students with this one, which is they need to be, this is the quiz at the end of the course, but not at the end of the lecture.
I guess the crossings at different depths.
Yes, the colors are different depths, right. So there's sinking in the North Atlantic. The most important addition to this for the purpose of this talk is that there's a Southern Ocean component to sinking. And you'd expect that. It's cold down here. It's cold up there. It's cold down there. Water sinks where it's cold. So although it doesn't sink very well in this cold spot, that's because it's too fresh. Anyway, there's lots of intricacy here, but here's the Southern Ocean, and it connects the world because it is a racetrack around Antarctica, because there's this open passage between South America and Antarctica. That makes all the difference for the dynamics of the Southern Hemisphere compared with the Northern Hemisphere. It means that water here is forced to cross deep and rise farther south to the surface and then come back. It's very difficult for warm water to make its way south across this gap. In the north, the warm water can go wherever it wants. What we need is a boundary to do that. Down here, there's no boundary. That's the difference. Of course, we know the ocean is much more complicated. Here's a result from a 1/6 degree model, but I'll skip over that. We're going to go back to even more simple. This is a way that people often look at the Southern Ocean. They pretend that the whole thing looks the same everywhere, and that if you do a cross-section from Antarctica north, basically up to South America, but anywhere around Antarctica, you'll get this picture. And the picture is that you have deep waters coming in deep and rising to the surface, splitting, some of them going to the north, and some of them coming back to the continent and getting even colder and sinking. So basically, your inflow is pretty deep and pretty cold. It gets colder to go to the bottom, and it has to warm up to go to the north. And the circumpolar current runs through that. Lots and lots of detail one could go into on that. I just want to point out that the real picture is at least three-dimensional and not just that zonal average. This is a picture of temperature on a surface that it's a density surface, constant density surface that rises up to the up around Antarctica, close to the surface. You can't see the depth of this, deep here. And then you see this warm water spiraling around and coming on in towards Antarctica. Where it comes closest, and then it actually spreads on into the Ross Sea here. Where it does that is where there's an awful lot of changes in ice sheet mass balances. This is a picture from Mignot et al. Showing how the Antarctic ice sheet changes. There's a lot of implication of these warm waters in the ice shelf, how the ice shelves come off and how they melt and break off. And that's a balance that's always there, but if you bring in more warm water, you're going to break off more ice. So it's part of the story of what's happening with the ice sheet. So that's kind of just a whiz through the Southern Ocean. This is an iceberg from one of the talented photographers. We had many talented photographers on that cruise. Not too much to look at. We didn't have no polar bears in the Southern Ocean. No penguins, no sea life. We had icebergs. Okay, the other thing I want to just go through quickly is the climate change. This is the other big thing that is part of what I've been working on. Not my own work, but I've been part of the IPCC process for the last 2 rounds, as have many of you. Points here are that global warming is ocean warming. And the heat is not missing. This thing called the hiatus is a surface temperature phenomenon. This is not new information. This is information that was easy to diagnose and put in this report. Not so easy. Dean Remick was part of this, and Greg Johnson. They put this together. Second, the ocean functions as a gigantic rain gauge. It's 70% of the Earth's surface. It's where most of the raining and it's where most of the water comes from that's going into the atmosphere. As it rains, it freshens. As it evaporates, it gets saltier. So if you rain more and evaporate less, it'll get fresher. And if you do the opposite, it'll get saltier. So by measuring the surface salinity and upper ocean salinity, we can see how the hydrological cycle is changing. So the ocean is a big rain gauge. And the third point here is that the ocean, because of the excess, the anthropogenic CO2, which is excess, and part of that gets into the ocean is acidifying. You've already seen this plot, so I don't need to spend much time at all on it. Here's the surface temperature. Here's the hiatus. That's the surface temperature record up through 2000, comes up, plateaus. Let's say there's no such thing as global warming. Okay. And we do see, as Walter pointed out, that there are bumps and wiggles here. We can also map out where the surface temperature change is concentrated. It's mostly over land. But where is the heat change? This is what we've documented in the ocean observations chapter in the IPCC. This is the upper ocean, the top 700 meters. This is the trend from 1971 to basically the present of the report. And that's because the data sets weren't that good enough before that, so Greg refused to make the calculation before that. It's mapped out very nicely. You see most of the world is warming, but there are areas that warm more. There they are. And areas that actually cool. And these are interesting patterns. Lots of interesting science in this map. If you look at this as a function of latitude, you'll see the warming extending to depth in the north. That's the North Atlantic. Where else is the ocean warm? Oh, and here was an important number. 77% of the extra energy in the Earth climate system that's due to climate change is in this layer. That's a lot. Okay? The deep ocean, this is a picture based on our hydrographic sections that we've taken for all these years. Warming is concentrated in the Southern Ocean. That's where our closest window to the surface is, and the water spreads out. Or there's less of it being formed, or something is happening. That's a work in progress for the community. What we can document is that 16% of the extra energy is in this deep ocean layer below 4,000 meters. So what we see is that most of the deep ocean is warming, and the warming is concentrated in the Southern Ocean. When we plot heat content of all the parts of the climate system, here since the 1970 up to the present. Let's see, atmosphere is this little teeny bumpy thing down here. Air doesn't have a whole much heat. It's a gas. Then we have the land. It actually holds a little more because there's water in the soil. Ice has water in it too. Here's the deep ocean. Here's the upper ocean. So you see that almost all of the excess heat is in the ocean, 93% of it. That's not true for the carbon. That goes into the atmosphere. The ocean does not suck up 93%. It's way less. But of the heat, it's going in the ocean. If you yeah.
But why don't you give data in terms of joule per cubic meter for every region? They're all integrated.
These are integrated because we want to be able to talk about this curve too, which is a global average. And also, there's a lot more uncertainty. You crunch down the uncertainty when you do average over bigger areas.
Right?
Pardon me?
There has to be less fluctuations.
There are, yes. So you integrate over big areas, and you get, here's the uncertainty bars. That's the dashes out here, the dash lines. If you took all this heat and put it in the atmosphere, we'd be at 100 degrees warmer. So that's a nice fact to take home to the family. And we also see no hiatus in this curve. Now, I have to say that Greg picked his favorite curve from Dominguez et al., which isn't even cited in some of these recent papers on hiatus. But the other ones may have a little twist at the end or not, and the uncertainty range is pretty large. We don't see much happening in ocean heat content. So the ocean is holding most of the heat. And it is important that the atmosphere, that we know what the atmosphere is doing, because that's where we live. But it's not where the heat is. Okay. And this is the recent paper that was just alluded to, Chen and Tung last week in Science. And they've plotted all these things. And you can see in different areas of the world, here's the global ocean, different layers. There's a rise all the way to the end. No hiatus in the ocean. And they attach that to a rise in the Atlantic back here around 2000, and then a rise in the Southern Ocean later on. So they've got the regional dependence. There is a lot of work on that. The ocean as a rain gauge. This is a plot also from this IPCC chapter. I did this late at night with my own Adobe Illustrator package. The map to focus on is at the bottom. This is the surface salinity of the world ocean, and the one above it is the trend in surface salinity of the world ocean since 1950 up to 2000. There's some similarity between these two maps, and what we can conclude from them is that the salty areas are getting saltier, roughly, and the fresh areas are getting fresher, roughly. Not one-to-one correspondence everywhere, but enough. And the contrast between salty and fresh has been growing, and that's statistically robust. This is consistent with a warmer atmosphere that is more humid, more moisture in the atmosphere. The atmosphere doesn't hold much water compared with the ocean. So you have an infinite supply of water for the atmosphere. If the atmosphere wants to hold more, it can get it. And when it holds more, it's in its own equilibrium, which means it's cranking it through. So it's going to be picking it up in one place and putting it down somewhere else. The exact scaling of that to the exact warming that we know has happened in the atmosphere is also an area of research, but this general idea of this salinity changes showing this consistency means that we can also see climate change going on in the hydrological cycle. That's important for starting to understand drought and flooding on land. I think this is my last slide from this IPCC chapter. It's possible now to plot, to map the global anthropogenic carbon inventory. There are different versions of this. This is the one that was chosen. And you see where there's color is where the anthropogenic carbon, so burning fossil fuels, putting in the atmosphere to reach equilibrium with the ocean. Some of that goes in. You're going to hear a lot about that tomorrow, I hope, because I'm not the one to explain the carbon cycle to you. Ralph will do that maybe, or Mark, or somebody tomorrow. Anyway, here's a map from Kadiwala et al. And you see most of it in the North Atlantic. This is deep convection. Actually, this is going all the way back to my first year work as a graduate student with Mike McCartney on the Labrador Sea. And then a big band in the Southern Ocean, which is not exactly the circumpolar current, but it's got a lot of interesting features to it, why it's that way it is. And then there's a lot of it going into the Arctic. Time series at Hawaii, there are very few time series to back this up. Very, very few. Here's one. At Hawaii, because of the IGY and Dave Keeling and persistence over decades of maintaining this and continuing persistence, thank you, the atmospheric CO2 going up, surface ocean PCO2, basically the carbon in the surface ocean going up, and the pH going down. This is measured since 1990. There are lots of projections of how pH will go. Some regions that are really going to acidify faster and that are the northern North Pacific, this coastal region here, and the Southern Ocean. So that's pretty much it for plots. I just wanted to say that it was an incredible pleasure being part of this process. I don't actually work on climate myself for research. I work on the large-scale circulation, but it was really important to be part of pulling all these things together. And Greg Johnson, kind of as he was going along, let loose this haiku for our chapter, which was lovely. And then he showed up with a little tiny book, and he'd done a watercolor for our chapter. And then it turned out he did one for every single chapter. So I highly recommend looking this up. This was for our chapter, and abyss warms. I've shown you that. The coasts flood. I didn't talk about sea level. Air moistens, salt patterns shift, and carbon sours oceans. Where do we go? This is one of the ways we're doing measurements in the Southern Ocean, very creatively. Forward. We need data to figure out what's going on. The observing system breakthrough, so this is the third breakthrough, I was only supposed to have two, is the Argo profiling network for the interior of the ocean. Satellites are absolute essential big breakthrough also for these decades. But within the ocean, this has made all the difference. Our students don't know that oceanography existed before Argo, which is great. It's a wonderful data set. And then there's these creative solutions. So this shows in the Southern Ocean where all the Argo data were for about a year. Here's an Argo float sitting at the surface after it's come up to talk. You see big gaps here. Oh, why are there gaps? Oh, there's sea ice. It's hard to measure down there. So these pinnipeds, this is the pinniped network, have been going around with CTDs on their foreheads, helping us. And they dive deep and make lots of profiles. This is actually a very important data set. One would hope to be able to eventually fill this all in, and we can. We have a way to do upper ocean Argo now under the sea ice. We cannot track without more money. We need a lot more money to be able to insonify and listen and track floats under there. Basically, now we just put them down, and they come up at the end of the next summer, into the summer. And we can now start to monitor the carbon cycle and ocean productivity, move towards a bio-Argo. The deep ocean is not covered with Argo. Argo goes to 2,000 meters, and I think that's just a design decision. And so now, as of this year, there's testing of Argo to the bottom, and that's going to start in several different basins. First, I think off of here, the experiment was out just recently. Just put the floats down. These will go to the bottom. They're more expensive, and they need more battery power. But it'll start allowing us to say something about deep ocean heat and temperature content. So back to the take-home messages. First of all, for science, when you look at every observed record, for instance, that surface temperature record, there's a lot of interesting stuff in it. You see what you see. And including the controversies, they can lead you down some really fun paths of discovery. And the hiatus is one such place. People are really looking hard at how the ocean works and how the atmosphere works top down. You know, what's the reason for this feature in the surface temperature? So this is the fun part of the science, the fun part of being an observer. The big picture coming from all of this work that everyone has been doing and all the measurements making is that there's unequivocal warming, even though there's natural variability. Hydrological balance is shifting. The oceans are acidifying. Ice sheets are starting to break up. I didn't talk about that. And there is sea level rise. And we need sustained observations to keep that going. So I'm going to finish with one more Greg Johnson haiku. This was from one of the later chapters in the IPCC. 40 years from now, children will live in a world shaped by our choices. So thanks.
Let's start with if anyone has a question for Lynn. Let's see, Heinz and then Vasilis.
I was surprised when I saw your chart where the carbon is concentrated, namely principally in the North Atlantic. Yes. There is practically no effect shown in the Eastern Pacific around China and Japan. Yes. Why is that? Do you have any explanations for that?
Yeah, that's related to this overturning circulation of the world. So the North Atlantic surface waters sink deep, and so they bring the carbon down with them, and that allows an inventory to build up because you're cycling through there often enough. The Pacific has very little overturn. It's pretty capped by its freshness, and so you're going to get the carbon in where you have younger water. It's water that is cranking through the system and cranking in deep. So the North Atlantic, that area of the Labrador Sea, convex to 1,500 meters, but not every year. There's certainly interannual variability, decadal variability, but it's new water, 10, 20, 30 years old. Pacific, you get below the surface, you're at several hundred years.
Okay.
Vasilis.
Yeah, what determines the scale size of the bio-Argo deployment?
Money.
Okay, interesting. But it's got to be a scientific.
Right now, 15 floats.
Yeah.
$70,000 of whack to have oxygen, nitrate, pH, and optical sensors to match with the chlorophyll, ocean color sensors.
Yeah, how many is enough is the question, really.
How many is enough? We're saying for the Southern Ocean, 200 is a good number. It's not, it's. When you actually see a float and think of all the water that float's supposed to represent, you worry a little bit. But it gives us really important information about that region because it's cycling every 10 days, or 5 days if we set it that way. And 200 of them will sample all of the important dynamical regimes and different productivity regimes south of about 40 south. To do the globe, so full Argo, TS Argo, is 3,000 to be a full array. And we're talking about maybe a third of that for a full array for the globe.
Roald and Margaret.
I have a somewhat different question. I don't know whether you will be able to answer. In research on some tests going on with carbon sequestration to help coal industry, what oceanographers are thinking about scenario of dumping carbon to the ocean floor?
Maybe somebody else should answer that, because I hear about it, but Ralph knows the answer. Yes.
One of our speakers from Toronto. Did you want to take that up, Ralph?
I can say it.
Ralph Keeling.
I mean, the idea of pumping carbon in the deep ocean was advanced probably a few decades ago, and it's mostly run afoul of the concern that it would affect organisms in the deep ocean, which on the face of it is a little strange because pumping it in the atmosphere affects the whole planet. But we have a law of the sea, and so we have international treaties to protect the deep ocean. We don't have something similar to protect our planet as a whole. So that's where it's stalled. And of course, there's continued discussion about pumping it into below ground in places near power plants or elsewhere. So that was just addressing that. That is still sort of on the research agenda. It just doesn't have a mechanism to pay for it.
Margaret?
With the El Nino, La Nina cycle, do you anticipate that the hiatus will terminate, and that will, and when? How soon?
Well, El Nino, it's more. This is more the decadal scale of the El Nino, La Nina. So that you're talking, El Nino is a 3-5-7 year cycle, but that's modulated over a sort of a decadal time scale, and I guess that's what's implicated here. This new paper last week says let's look at the North Atlantic and the Southern Ocean instead as the places where the heat has really been taken up. And I would agree with that idea also, to look there. And that's again a decadal, that's what you're seeing is a natural variability. It's either the El Nino La Nina cycle over here, or there's a big decadal variability in the North Atlantic called the North Atlantic Oscillation that swamps anything that we can measure for trends in the northern North Atlantic. The Southern Ocean has another big mode. These are natural modes of the coupled climate system. And so they have their own sort of chaotic, it's a very broad spectrum, but with a peak someplace around 10, 20, 30 years.
So that it's possible that the hiatus will continue for a decade?
Well, it went away before.
I think,
Yes.
nothing is forever. I'll jump in on this one. This is going to be a matter of active controversy for the next couple of years. But the basic point is there are only a few places in the ocean where you can force warm water down into the depths. And there's the Antarctic, there's the formation of the North Atlantic deep water, and the Western Pacific, which is the destination of the El Nino waters that are blown across the Pacific, La Nina waters, which are blown across the Pacific by the trade winds. The Western Pacific is as hot and as elevated as it has been in years, and NOAA started off by predicting that there would be a large El Nino relaxation of the system, where all the hot water that's piling up can't all go underneath, and so it'll flow back across the Pacific. The one reason I am suspicious of their prediction at the moment is that there's another paper out that shows that the trade winds which drive the La Nina cycle, the trade wind stress is 2 to 3 times larger in the forcing sense, subduction forcing sense, than its historical average. And so if their predictions are based on empirical experience, they may be wrong. The trade winds may, in fact, I don't know. I'm not going to make a prediction, but the one thing that's different about this prediction as opposed to the one 15 years ago is the strength of the trade winds. I guess I'd put it that way. So I have Jeff, then Lynn has to leave, and I'm going to make a remark, and then we're all going to go for food. Yeah. Is there somebody else? Walter, are you also? Yeah. Okay.
Okay. So the use of the ocean as a rain gauge. I guess the question is, if you're to integrate a really interesting number is the global integral of the precipitation on the ocean minus the evaporation, because that number has to be also the runoff from the land.
That's correct.
And I guess the question is, how robust do you think this measurement of precipitation by salinity is, and what sort of numbers are you getting if you do that global integral?
The global integral, so this is interesting. The IPCC was on the AR4 as well. Sid Levitas was part of our team. He came in with salinity trend maps. This is before there's Argo data, so you could still see it in the historical data. And he was showing salinity trends from Tim Boyer at NODC. And we said, is there any signal there? He said, no, it all integrates to zero. There's no signal to talk about. Oh, but if you look at each ocean, the Pacific is freshening, the Atlantic is getting saltier. So you're getting a redistribution. That's the normal distribution. The Atlantic is a salty ocean, the Pacific is fresh, the Indian is salty. And normally water is picked up from the evaporative basins and put in the fresh basin. And what was happening was that has gotten stronger. That's a zonal redistribution of
but some
water.
of it goes onto the land and then goes into the ocean.
It's tiny. It's not tiny, but it's not. It integrates out. The only way you'll see a mean change in the salinity is from introduction of new fresh water. I think basically from melting.
Which was big in the past and not so big yet now.
Very big in the past, not big enough to detect now.
Yeah.
Yeah.
So Lynn, I'm going to let you go.
Thank you.
And thank you. Yeah, okay, right. And so now we'll take some more questions until you all get tired. And go ahead.
This is, again, slightly off on a bit of a tangent, but there's been a lot of publicity recently about plastics in the ocean and getting into the food chain and so on. This is obviously not directly connected with temperature and salinity and so on, but how seriously do you think that is quantitatively now?
Do we have a marine ecologist here that could, what we know is that the plastics that we all put into the ocean are convected towards the center of the Pacific and get trapped in a gyre in the middle of the Pacific. And it's not plastic bags that you see floating on the top of the ocean in the middle of the Pacific. By that time, the sun has broken up all these plastic bags into little pieces that fish eat. So they're actually more dangerous, and and it's unretrievable, basically. So the question is, quantitatively, how big a quantitative threat is that to the living biota in the Pacific Ocean? And I don't know the quantitative answer to that question. Does somebody know it? We're going to have marine ecology tomorrow. Vic, maybe you can ask somebody around and see if we can get an answer to that one.
You want me to take a crack?
Yeah, if you're ready, Richard. Richard Norris.
There's actually a microphone. Oh, okay, that's good.
Hold it up.
I have to.
Hold it up.
I don't like this. No, I think, so there was just recently an Algalita expedition to the so-called Pacific Garbage Patch. What's that?
Hold it up.
It does work. Does it? No. Okay. Yes, I was trying to boom out, okay? Anyway, and they found a lot of tsunami debris, as it turns out, from the Japanese tsunami 3 years ago. And so there is actually floating material out there. Charlie's right that most of it is really small material that is confined principally to the surface ocean. But it is being taken up by fish, and actually Scripps research during the Seaplex expedition showed that midwater fishes are eating this plastic, and they in turn then get eaten by other organisms too. But I think we don't really know what the actual impact is in terms of the food chain. It's probably a bit premature to say that there's a really severe negative impact of that. There has been studies out actually in the California coastal waters based upon Cal Coffee studies. And it's very clear that the plastic issue is a post-1970 thing. Okay, since the 1970s, we see more and more plastic in coastal waters. And the vast majority of what is in the deep ocean is from land-based sources. And I think that's all I should say.
Well, thank you. Okay, I'm about ready to call the question, but I'm going to issue a challenge to the people that I heard today, not to answer this question today, but to do so tomorrow, because my talk will also be on the implications of the hiatus. And in particular, David Victor and I have submitted a paper to Nature which suggests that the 2-degree surface temperature goal that the climate negotiators are working on is meaningless, and that they're all negotiating for the wrong thing, and this will not be popular. But we also suggest that there are 2 more fundamental measures of the actual impact that humans are making on the climate. One is ocean heat content, and the other is something that Francisco wanted to measure, which is the radiation balance at the top of the atmosphere. And both of these are more fundamental measures of the energy going into the climate system, which then redistributes it in incredibly complicated ways. And so what we want to suggest is that, that we have a technical conference that reviews the readiness of these 2 measurements to become indicators for the global climate negotiations. And so, it's a technical issue. I don't know how ready they are, but people here at Scripps and others do know the answer to that question, and we can have a discussion about that tomorrow. But today, we have a reception that I presume they're out there. The door's been closed. Or if the food is there. So let's all go and thank you.